All right. Happy Monday, everyone. Today we'll be talking more about sedimentary rocks and then doing some test review. And I went for a walk this morning and saw that there are flowers coming out of the ground here in Burlington. So go take a walk outside today, get some fresh air. All right, so logistics for this week. There is no lab assignment due this week, but there will still be some other things that are going to be due Sunday at 11:59 p.m. as normal. Okay, that includes the quiz from today. There will be no quiz on Wednesday, but I will post a video of me explaining directions for the exam. Okay, and then Friday I will continue with sedimentary processes. Okay, so that'll be a lecture. You also have a reading quiz for chapter 14, streams and floods, this week. Okay. And then the second part of the lecture today, I will talk more about exam details. So at the end of last week, we talked about different sedimentary environments and how sediments that are eroded and transported and deposited are deposited in certain types of environments, whether it's glacial, it's in a lake, it's in a desert or a river, along the coast or in the ocean. And the characteristics of those sediments tells us about where they accumulated and how they accumulated. So we can use sediments and sedimentary rocks to reconstruct what the surface of the earth was like in the past. This is what makes it possible for us to look at fossils and sedimentary rocks and reconstruct what the earth used to be like millions of years ago. Okay? So we'll start today talking about terrestrial sedimentary environments. So terrestrial always refers to things that happen on land. Okay? So these are sediments that accumulate on the dry land surface or in freshwater basins, and a basin is just somewhere like a bowl-shaped area, somewhere where sediment settles out. Okay? And the physical, chemical, and biological characteristics of those sedimentary rocks are very valuable for understanding what the surface of the earth was like in the past. And we'll consider 6 types today and go over them in detail now. So glacial, mountain streams, alluvial fans, deserts, rivers, and lakes. So we'll start with glacial environments, but you guys already know this, right? So glaciers are highly erosive, and so they produce a lot of sediment and transport them. And just like we learned earlier in this class, right, is that, glaciers where they transport debris of all sizes, unsorted, unstratified, on top or below the ice surface is till, right? And you could have tunnels of water that are pulsing sediment beneath the ice surface, making eskers. The glaciers push out these big ridges that we call moraines, right? And sometimes between a moraine and a retreated glacier face, you get a glacial lake, or possibly in front of the glacial moraine. Downstream of a glacial moraine, right, there's a bunch of meltwater being produced by the glacier or a draining lake, and that creates a outwash plain. And so these are big rivers that flow across the landscape, transporting sediment that was ground up by those glaciers. And so if we look at this big outwash plain in Mount Cook National Park in New Zealand, you can see that there is the active river plain over here, right? And there's old inactive river plains over here, right? There's active rivers with flowing water in them right here. And you can see the outlines of the old meandering rivers on the inactive part of the plain. And the important thing to remember with outwash and all glacial sediments is that they fill in the eroded area, right? So if you dug all the way down to the bottom of the glacial sediment in a glacial valley, and you took an elevation profile of where you hit the hard bedrock beneath all that sediment, you would reveal the U-shaped topography of a glacial valley, right? Okay. So now what about glacial sediments as rocks, right? So we know a lot about glacial sediments that are on the landscape today because glaciers were here not that long ago. But we can also find glacial rocks in the geologic record that are much older and lithified, meaning they are hard rock. So some of the more famous ones of these are those that are over 600 million years old that show us that the entire Earth was covered in glaciers and sea ice called these snowball Earth times. And we can find glacial till in these ancient rocks all over the world from that same time period, from Namibia, from Norway, Greenland, even some in North Carolina in the Appalachians. So we can also go to other places around the Earth and find younger evidence for ice ages, right? And these are like rocks in the Transantarctic Mountains from the Carboniferous and Permian times, when we also had a big ice cap covering the southern hemisphere. And remember that the discovery of these glacial rocks was one of the key observations that Alfred Wegener used to propose continental drift. Okay, so let's go to another mountainous area where there are no longer glaciers, or there are no glaciers to begin with, in mountain streams, right? So the main characteristic about a mountain stream is that it's very narrow and it's surrounded by steep slopes on all sides. And so the way that sediment is brought into this stream is through debris that is falling off of the mountain sides. So big boulders will fall off and land into the stream bed, and then flash floods, extreme melt events from snowfall can transport those big boulders downstream in flash flooding or in big debris flows. So we can get a wide range of grain sizes in high mountain streams because we are so close to the source region. So we can have big boulders all the way down to ground up silt and clay, mud. As streams flow downhill, they're going to take the finer sediment, the lighter sediment that's easier to transport, and it will deposit the larger grains in any flat areas that form out. So what's interesting about mountain streams is that these are typically very rare rocks to find because mountains, right, you have a lot of erosion going on because there are steep slopes, so there's landslides because of gravity, and there are steep stream gradients that are transporting those rocks and sediment downhill. So it's quite rare for us to actually find the rock record of past mountain streams, but it is possible in some places. And if we did preserve it, we would find conglomerate or breccia, right, which is that mixture of large grain sizes. So just another thing about high mountain streams, right, is if you have ever been whitewater rafting or whitewater kayaking, the whole concept of the whitewater, the rapids, right, that is created by boulders, so the large grain sizes that are in mountain streams. So, this is a reflection of the sedimentary processes where you have a steeper gradient, higher energy streams that are going to be moving these boulders that are falling into the river from the mountainsides, and that makes for what's fun about going down in these rivers and whitewater rafting. Okay, so the next sort of high slope environment are alluvial fans. And alluvial fans are fan-shaped, right? So I found the weirdest example of a hand fan that I could find, and it's this really ugly pugly fan. So fans are literally shaped like this, right? Sort of this semi-circular wedge that emanate out from the bottom of a steep, narrow mountain valley, and sediment is being deposited out on the landscape below. Okay, so there are streams that are coming down these narrow mountain valleys, and they're carrying sediment, and it'll come down through here and deposit sediment, and then too much sediment will build up, and so the stream will move over a little bit and build up over here, and it goes back and forth, back and forth, back and forth, building up a fan, okay? Right? So we typically find these in areas where you have very steep topography and then a very gentle mountain valley in between them. Okay, so if we were to dig into a alluvial fan, you would find grain sizes that are coarse. So it'd be sand up to cobbles and possibly boulders. And if that turned into a rock, you would have breccia or conglomerate, or a arcosic sandstone, which is sort of an unweathered sandstone. So just to show you guys what these fans look like on the landscape, right? So we have this image here, which is from Arthur's Pass, New Zealand, or nearby in Canterbury. And we have this steep valley, right? And then there is this perfect fan shape right here. There's another one right here. And then there's also one right here. Here is an example of a fan from Death Valley, right? So here's the steep, narrow valley, and then it spreads out into this perfect fan shape, okay? There are the fans, and now you can see it with an actual fan laid out on top of it, okay? So desert environments, okay? So now let's go into a place where there's not a lot of water, all right? Because there's not very much water and it's dry, they lack vegetation. So with the lack of vegetation, the soil and sediment is very easily mobilized by wind. In desert environments, you typically transport sand-sized sediment, and you can often get a really reddish color because the sediments are oxidized. And you build up sand dunes, right? So you saw this in Lab 8 by looking at that question about Arizona, but there are other very famous sand dunes like those from Tunisia, or these huge dune fields in Namibia in southern Africa, where in this dry stream valley, there are all these dead trees against these bright red sand dunes. It looks pretty surreal. And remember from our sedimentary structures lecture that when you have blowing sands as dunes, you create structures called crossbeds, which are preserved in the rock record. And so the most spectacular example of this is in the Navajo sandstone in the Vermilion Cliffs of Arizona. And the erosion of this landscape has exposed this like amazing crossbedding texture in the rocks. Another type of environment is a river environment, and in geology we refer to river environments as fluvial. So rivers deposit fluvial sediments. So rivers can transport a variety of grain sizes, but typically from clays up to gravel in larger river plains, okay? And in steep rivers, you can transport boulders, right? We've seen that if you've gone hiking up high in the Green Mountains, you've seen large boulders in the stream valleys. And so the key here is that the stream velocity, right, and the gradient of the slope is what's going to help determine what grain size is deposited. Over time, rivers will meander and spread out across the flat part of the landscape and depositing sediment, right? So the floodplain is that area where the valley is flooded by rivers through time and deposits fine sediment. So here in New England, if we look at where many of the farms are, right, it's not on the steep slopes of the mountains, it's in the flat floodplains of the rivers. So if you go down to the Intervale, right, and that's a great place to go running because it's very flat, right? You are running on the deposits of silt and sand that the Winooski River has deposited through time. If you go up to like the Lamoille River further north of here, you can see that the hillsides are all really forested, but humans are still doing agriculture on the flat floodplain along the rivers. We will talk about rivers in greater detail in a later lecture because they are relevant for understanding how flooding works. And this time of year, especially in New England where we have snowmelt, flooding is quite an important process to understand, okay? And there's many different types of river environments that we can study, not just the ones that we see here in Vermont or New England where we have meandering rivers, but also really big rivers like those draining the Himalaya or those in Alaska that are transporting much larger volumes of sediment in really active tectonic areas. So going downstream from a river, right? If a river slows down out into a big basin, which we call a lake, it deposits sediment which we refer to as lacustrine. And lacustrine sediment is typically fine-grained, right? That's because as that river, which has quite a bit of stream energy, is flowing out, right, it's going to carry a greater range of sediment sizes. But once it reaches out into that larger lake basin, right, the water speed slows down, and so the coarse grains, the sands and gravel, drop out right at the mouth of the river in the delta, but the silt and clay stay in suspension and float out into the lake. So if you have been out to like the bridge that goes over the Winooski on the waterfront, and sometimes in the summer or in the late spring, you'll look out and see that the water coming out underneath you is pretty brown, but further out in the lake it looks more blue. And you are seeing the plume of sediment that's being discharged out into the lake. If you take an X-ray of sediments on the bottom of Lake Champlain, like this one, where you use sonar to map out the different layers of sediment, you'll see that lake sediments are deposited in what we call laminations, very thin layers or beds that record changes in the lake through time. So lakes are probably the most important climate record that we have on land because they record a variety of processes continuously. We don't have to worry about things being eroded away. And we have lake sediments that we can look to from different parts of the geologic record, right? But our oldest present lake, active lake, is in Russia, Lake Baikal, which is basically the border between China and eastern Russia. And it's almost up to 13 million years old at this point. And then we have younger ones like Lake Champlain. So we can go into the geologic record and find examples of former lakes that used to cover large areas. And one of those is in southern Wyoming and northeastern Utah, where a big lake 50 million years ago deposited a bunch of fine-grained silt and sand and some spectacular fossils, which I forgot to paste into this lecture, but I'll do it next time, okay? And then next day we will talk about, or next lecture day, so on Friday, we will talk about marine sedimentary rocks. So marine sedimentary rocks are much more common, and they record a much older and distant part of Earth history. And so why is this? Well, once sediment makes it out into the ocean, right, it is less likely to be eroded, right? There aren't surface processes of erosion, like mountain building or rivers plowing through, or even humans coming and disturbing the landscape, right? That sediment is going to sit on the seafloor, on the ocean crust, for millions of years, probably until it is subducted back into a trench. So it can be hundreds of millions of years old. And where we have sedimentary rocks that have been uplifted by mountain building events, we can go back billions of years. Okay? And we'll talk about the different types of marine sedimentary rocks in the next lecture. All right? So we'll do that next time, but what I wanted to go over now was the exam, right? So I want to talk about policies. So I will make the exam available on Wednesday at noon, and it will be available until 5 p.m. on Friday. I'm making it due on Friday at 5 p.m. because I want to be able to answer questions during the work week and I don't want you guys working on this on Friday evening. And I'll talk about the next point, right? So this is going to be open note, open book. You can use calculators. There won't, I mean, any of those tools are fine, right? I'm not going to be asking you to do really hard math at all, but there may be like a math question about radiocarbon dating for determining the age of something, okay? The trick is, though, is that you need to be doing this on your own, right? You cannot work with others, and you will sign an honor code agreement testifying to that. You will be given an hour to complete each exam attempt, right? And you will get 2 attempts, and the highest score will count. I will, if it's possible in Blackboard, make it show which questions you got incorrect, but it will not show the why, like your specific answer, why it was incorrect or what the correct answer is. So you'll know what you need to go back and correct, but you will not just be given the answer, okay? I'm not still sure about how partial credit can work on Blackboard, but I'll try. If there's any way to award partial credit for just completing or doing any part of a question, I will try to do that, okay? And then back to my first point, right? So if I'm going to give you 2 attempts, which can give you an hour, that means that you need to start this no later than 3 p.m. on Friday. Please do not wait, right? I'm giving you over 48 hours to do this, right? And then finally, if you have a conflict, right? I know a lot of you are in upper level classes, right? And you're dealing with a lot of hard stuff right now, school and coronavirus related. Please contact me like as soon as possible if you need to reschedule when to take this. I'm totally willing to be flexible here because I know things are really shitty right now. So just let me know, all right? And then for the exam review, all right, here are some of my tips, okay? What I would do if I were you is study my slides and know where the information is on them, all right? Review the reading quizzes from the textbook. I will use questions from those quizzes. Review my iClicker questions and Blackboard lecture questions, right? So like simple things from lecture that I've done in the past, okay? And then use my review guide. And just so you guys know, the material that is a game for this exam is days 13 through 28. I know that sounds like a lot of days, right? But in the following slides here, I will go over exactly what you need to know. So the rest of this slideshow, which is posted on Blackboard as PDFs, I will just make available. I'm not going to go over this word for word right now, but if you come to office hours today on Blackboard, you can talk about these things. But just I'll flip through a couple of these really quickly and just like show you that, you know, what I've posted in the study guide on Blackboard, the Word document, I've pasted again into this slideshow and just like kind of annotated with pictures what I might be talking about, right? So like for geologic time, right, you need to know the 5 principles of geologic time and what they mean, right? So over here, cross-cutting relationships. So if you just search this on Google and try some of these puzzles on your own, that'll be helpful, right? So just search cross-cutting relationship puzzle on Google and try and put these in order, right? And identifying unconformities, right? So here's an angular unconformity. If I gave you a picture like this, you should be able to identify that. Numerical dating, right? So here's a radiocarbon half-life curve, right? So 50% is left after 5,700 years. So I would ask you to, like, if I said how many years have elapsed if 2 half-lives have happened for carbon-14. So 2 half-lives, 50% is gone, 50% of 50 is 25. So 11,460 years would be y, okay? Stuff like that. Knowing what the difference between beta and alpha decay, okay? So, and then geologic time scale, right? Knowing these subdivisions, right? So being able to fill in the blanks on something like this, as well as extinction events and knowing which are the major ones, right? And what like the biggest one is. Plate tectonics, knowing what Alfred Wegener's observations were that led him to this idea, as well as the major topographic features of the ocean floor. So if I gave you a hypothetical profile like this, you'd be able to label the major features you saw. Okay. Plate tectonics, the main points of evidence for seafloor spreading, right, which are summarized here. The review of the oceans, right? So what are the different types of crust? What is the crust made out of? The lithosphere versus the asthenosphere. And then what behaves rigidly, what behaves plastically, right? That's rigid is the lithosphere, plastic is the asthenosphere. And then what are the differences between ocean and continental crust in terms of density, composition, and age? What are the main principles of plate tectonics? That's in a lecture. What are the different types of plate boundaries, right? Divergent, convergent, transform. And then, what's the difference between a active and passive margin? Which type of crust subducts, what does not? And, just like these general plate motions, you need to know why the ocean plates spread apart, right? And you also need to know what type of collisional environments can exist, right? These three different types of continent-ocean, ocean-ocean, or continent-continent. You need to know the rock cycle, right? So I know this is like just a funny diagram maybe, but you need to know the different rock types, right? And what processes can link them together, what can recycle them within the same, okay? Magma and igneous rocks, right? So you need to know why magma can form, right? The three different ways: depressurization, volatilization, or heat transfer. And then what is the different types of melt composition, right? So which is really dependent on the silica content, right? And what we name them, ultramafic to felsic rocks. And then you need to know about igneous environments, right? So intrusive, which are plutonic rocks, extrusive, which are volcanic rocks. You need to be able to name the different rock types, right? So low silica to high silica. You need to know what controls the viscosity of magma, which is related to its silica content, and be able to identify what a sill is versus a dike versus a laccolith. And then for extrusive volcanic rocks, you should know what relates the shape of a volcano versus its magma chemistry, which of course is silica. The different types of eruptions that we can have, and the tectonic environment, right? So knowing these, right? It's an island arc, continental arc, a rift, a hotspot, or a mid-ocean ridge. And then the hazards, right? Okay. And then finally, and this will be maybe only a couple questions since we're just starting this, is weathering, right? So what's the difference between physical and chemical weathering, and what controls physical and chemical weathering on the landscape, okay? All right, I will be on Teams to talk about this.